So in the pre-class video notes, you saw kind of if you have these things here, like we did for the parametric curves, basically just divide through by this dx dt squared here in the numerator and the denominator. You can get this equation here, or likewise, you can divide through actually by the dy dt sort of deal and rearrange this and essentially get this right here. So you can integrate either with respect to x or with respect to y. And that's great. We'll see a few instances of integrating with respect to y as well. Of course, we've did this a little bit in calculus 1. And we've, just basically have to attune your eyes a little bit and use y's instead of x's. But otherwise, it's not so much different. So these are the formulas right here for our arc length, and we apply them in a variety of different situations. So we saw a few examples. I guess the only other thing, and this is a little bit of a proof of this theorem here about why the arc length formula works and why it is the way that it is. But we also do get this function here in calculus 2, the arc length function, and this ends up being quite important in calculus 3. It turns out, some of these things, if you don't parameterize your curve with respect to arc length, with respect to s, which we have here, then you wouldn't get unique answers, right? So the answers would really depend on how you parameterize the curve and all that sort of stuff in calculus 3. And so that's a little bit strange. And so with the arc length function, though, everything works out grand. And so that's kind of why we're introducing this here along with arc length. The other thing that this kind of helps with, if you needed to compute many different arc lengths, all with the same starting point, but you didn't know maybe what your ending point was going to be, well, this essentially just leaves that ending point as a variable. And then you can go ahead and plug in whatever you'd like after the fact. And so it is kind of a convenience thing as well. But again, it'll get used a lot in calculus 3. We'll have S and DS in particular in calc 3. So, but it comes up here. Okay, so that is arc length 8.1 in a nutshell. Let's go ahead and take a few questions here before we start in on our problems for today. Doesn't look like we have any raised hands right now. Anything going on in the Q&A, Yuan?
Yeah, someone's asking, is it worth it to go through the rest of chapter 8, even though we don't go over this semester?
I wouldn't say so. Chapter 8 doesn't really get picked up in calculus 3 or anything like that. You need a higher dimensional arc length function and all that, and it's really more built off of the parametrized stuff. And so, yeah, I would probably say no, all things considered.
Okay. And there's another one asking about the quizzes and final exam. Will we be able to print out blank graphs to save time when plotting points?
Blank graphs. I haven't had this question before. Blank graphs, yeah, I guess there's no harm in it if you'd like to do that. I don't think it's going to be especially necessary. But yeah, I mean, that can save you at least the time to do that, right? So I'm not sure if it's a ton of time saved, because again, you may not have it to the right scale or whatnot. So I'm not really convinced that you'd be saving a lot of time, but I also don't see any harm in it. Again, you would have to show the webcam and whatnot, your paper at the beginning of the exam, just to make sure that you don't have anything extra on there. Good. Maybe one more question if we have it before we jump into the new stuff for today.
Yeah, and the final formula sheet and post survey, is it posted or not?
Yes, both of those things are on D2L right now. So the formula sheet would be under assessments near the final exam. So in that same folder where you have the final exam, you also have the practice exam, for instance, that just got posted earlier today. So you can take the practice final, and there's also the formula sheet there as well. And the post-course survey right now, I think the only link to it is on the under the announcements. There may also be a link to it someplace else, but I haven't really gone searching for it yet. But there is a link for the post-course survey under the announcements on the main page there. All right, one raised hand, and then we're going to get into the problems for today. Ian, you have the floor.
Hi. For the survey, are we supposed to wait until the class is like completely over? Are we allowed to do it any time starting now?
Anytime starting now is fine. You have enough of this class under your belt, kind of that you have a general idea of how things ran and what you liked and what you didn't like and all that sort of stuff. That now is a fine time to fill out the survey. It is due, right? We can't have anything due on these study days, right? So it's intended to be open the last week. And so we kind of took that to be the 14th through the 21st. So it's due on Wednesday, the 21st. Because again, we're not allowed to really have anything due on those study days, that Thursday and Friday. So make sure you do it before, well, Wednesday, the 21st, you know, in the evening or something.
Okay, thank you.
Yeah, no problem. Okay, so with that, why don't we go ahead and get into the new stuff for today. First up, find the exact length of this curve here, y equals 6, x to the 3/2 power on the interval from 0 to 1. So again, the big thing here is that we need to remember our arc length formula. In this case, because we have y as a function of x, we're going to go ahead and be integrating with respect to x's. So I'm going to have a dx over here, which means my bounds need to be x values. So this is excellent that it tells me that, you know, this curve exists on the interval from 0 to 1, right? So those are x values. Those are going to be my bounds there. Then we're going to have the square root of, and I'm going to go ahead and put my 1 first, and then we have a quantity squared, and what goes inside there is just the derivative. So I need to go ahead and calculate out over here really fast the derivative. So dy dx of our function. So we're just going to use a quick power rule here. 6 is long for the ride. The 3/2 drops down. We reduce our power by 1, so we get x to the 1/2 power. Of course, things simplify a little bit. And we can write this as 9, and the square root of x would be the same thing as the 1/2 power there. So that right there is my derivative, and I can throw that in. Okay, now let's take a line or so to simplify this before we integrate. So let's see, when I square the 9, I'm going to get 81. And when I square the square root, I'm going to get, well, just x there. And now we can see, thinking back, you know, this came right after chapter 7, you know, chapter 8. And so you just, you know, supposedly got done with a section of integration and whatnot. And here's another thing you can do with integration, right? You can evaluate stuff like this. And so technically you could get any sort of, you know, the techniques that we got back in our chapter 7 days in these sorts of problems. Usually, though, I've found as I look at these problems is that they're usually fairly nice. They're usually kind of some u substitutions, or there's some fancy way that you can take care of the square root. Worst case scenario, though, well, with the square root there, we've been conditioned to really think about trigonometric substitution. So the worst case, you may have one of these or so on the WebWork homework where you have to do a trig sub, but otherwise, hopefully there's a fast way to take care of this. So in particular, in this case here, right, it's going to be a u substitution. So if I do u equals the inside stuff, 1 plus 81x, then we have du is going to be equal to 81 times dx. So if you'd like to, we can go ahead and rearrange this and say dx is the same thing as du divided by 81. And so let's go ahead and substitute some of this stuff in. And so instead of the 1 plus 81x, well, I'll put my u, and instead of my dx, I'll put du divided by 81. Now it's kind of up to you. Remember, you're always kind of allowed to do u substitution in 2 different ways. You can either change the bounds to u values, or you can just evaluate out the indefinite integral, plug back in x, and then you would evaluate at those x values, 0 and 1. I'm going to go ahead and do that way, but if you'd like to change your bounds to u values, you certainly can do that as well. All right, so when I go ahead and I integrate this, well, the 180 first is going to be along for the ride. U to the 1/2 power is the same thing as that square root there. So when I integrate, I need to raise my power by 1. So instead of 1/2, it's going to be going to 3/2. Then I multiply by the reciprocal of my new power there. And that gives me the correct antiderivative. And now let's go ahead And well, we'll simplify a little bit, and we're going to resubstitute back in. Instead of u's, we're going to put our x's. So 1 plus 81x. Everywhere I see a u, and we have this raised to the 3/2 power. And this is what I was saying. I'm going to switch back and then evaluate at my x bounds. So x equals 0 and x equals 1. If you'd like to, you could have swapped in for u and then evaluated at your u bounds, which, by the way, if you plug in x equals 0 here, you would get that u would be equal to 1. Right? And you just use this transformation equation. And if you were to plug in x equals 1, the equivalent u value there would be, well, 1 plus 81 would be 82. And you would get the exact same answers that we're going to get here. So let's go ahead and evaluate this out for our final step. So again, 2 over 243, this constant's along for the ride. When I evaluate at 1, we're going to have 82 raised to the 3/2 power. And when I evaluate at 0, we're going to have 1 raised to the 3/2 power. Well, 1 raised to any power like this is just going to be 1. So this right here will be my final answer. And of course, you can even see in our final answer here, the 82 and the 1, that you would get, if you switch the bounds earlier rather than later. So either way you do this, you get the same correct answer there. Okay, let's take a quick question and then move on to example 2. Michael, you have the floor.
Hey, Professor McCombs, how's it going today?
Pretty good. How about yourself?
Pretty good. I have a question. So why would the second piece just be 1? I'm confused.
So when we plug in 0 into our equation here, right? So when we plug in 0, you get 0 times 81, which is 0, plus 1, right? So, okay, you have 1 inside of this raised to the 3/2 power. So if you cube it and you take the square root of it, right? Everything here is happening to the value 1, right? Well, 1 cubed is 1. The square root of 1 is 1. So at the end of the day, right, that answer is going to be 1.
Oops.
Oops, wrong button there. Does that help?
Yeah, that helps. Thank you.
All right. Yeah, no problem. Good. Why don't we go ahead and move on to example number 2. Find the length of this curve here. Notice that in this case, I have x as a function of y. So x as a function of y, that means when we go and we use our arc length curve, we're going to use the other one where we're integrating with respect to y's instead of with respect to x's. And that's good though, because right, we have these nice bounds for y. So these are going to be my limits of integration. We're going to integrate from y equals 1 to y equals 8. And again, we're going to have a square root. We're going to have 1 plus some quantity squared here. And again, this is going to be the derivative, but now we're taking a derivative with respect to y. So let's go ahead over here. And this is really going to be dx dy. So the derivative of x now with respect to y. And let's see, the 3/2 is going to be along for the ride. When I take the derivative of y to the 2/3, right, the 2/3 is going to come down and we're going to reduce our power by 1. So we get y to the -1/3. You can see there's some nice cancellation here. And that +4 doesn't really do a whole lot, right? That could be really anything there. But when you take the derivative of a constant, it's just 0. So, okay, we're going to have y to the -1/3 here. All right, so this right here is what we need to evaluate. Let's go ahead and maybe rewrite it a little bit. Simplify things down. 1 plus y. And remember, whenever you have powers raised to more powers, these simplify a little bit, and we could write maybe they multiply, and we could get y to the -2/3 there. Okay, so now we sit and we stare at this for a little bit. And I don't know about you, but this one looks a little bit complicated here. And so we need to think about, okay, how could we maybe rewrite this? How could we figure out some way to solve this? And so I'm going to go ahead and think about rewriting this negative exponent as division here. It's just something to do. because again, kind of, I don't know, we haven't seen anything exactly like this. So I'm going to write this as 1 divided by y to the 2/3 power. Y to the 2/3 power there. And okay, that's not looking great still. Why don't we go ahead and get a common denominator, right? That's something that we used to do back in, our algebra days. So I'm going to go ahead and get a common denominator next. So I'm going to put a y to the 2/3 power in both the numerator and the denominator here by this 1. So y to the 2/3 power here and y to the 2/3 power here. Again, in the numerator and the denominator. So I'm not really changing anything. I'm just rewriting this. And so then we'll have this common denominator and we'll have, let's see, this y to the 2/3 on top plus 1. And okay, well, now we have a perfect square in our denominator at least. So I'm going to go ahead and rewrite this. I promise this is going to be my last step before we actually get to the calculus of this problem. So I'm going to keep the top bit inside of the square root. Can't really do much to this right now. And then in the denominator here, when I take the square root of y to the 2/3, right, this would be the same thing as the 1/2 power. And so this makes it y to the 1/3 power, right? So the 1/2 times the 2/3, they cancel a little bit, again, multiplication. And so you get that cancellation of the 2 and you just get y to the 1/3 power. Now this is all positive values for y, right? 1 to 8. So you don't have to worry about any absolute values or things like this. Okay, now that we've done all of this algebraic manipulation and moving things around and whatnot, now it's really time for the calculus. Now it's time to integrate this. And luckily with all of this manipulation, notice what we have inside of the square root here. If you were to take the derivative of it, this is exactly what we have lying around here. So that is saying that a u substitution is going to be perfect for this. So I'm going to go ahead and do a u substitution, right? Maybe it wasn't obvious back here that a u substitution solves this, but now that we've done kind of some algebraic manipulation here, we can see that yes, a u substitution will work well. So let's go ahead. If I let u be my inside function, then du, well, when I take the derivative of this, again, we get the 2/3 coming down. We reduce our power by 1. And the derivative of 1 is just 0. And so this is going to be dy here. And so like I said, all of this right here, the y to the negative 1/3 power, remember that's just means it's secretly, in the denominator there, along with the dy there, right? All of this together is going to make du, or I guess I could rewrite this and it's going to really make 3/2 du, right? So I'm going to put my constant on the other side. And again, all of this stuff here is exactly what I have. So now let's go ahead and plug these things in. So again, let's see. The square root, this is exactly what I was calling u here. All of that other stuff makes 3/2 du. There we go. Now I can go ahead and integrate this. So the 3/2 is along for the ride. And when I integrate u to the 1/2, I'm going to raise my power by 1. So it's going to go raise the 3/2, multiply by the reciprocal of that new power. So it's going to be 2/3 there. And yeah, some things cancel. That's quite nice. And of course, you can always be paranoid, especially if this was a quiz and exam. Take the derivative of this, double check that you get back to where you started. Okay, so this is a good antiderivative. Now we're going to go ahead and plug in. Everywhere I see a u, I'm going to put this y to the 2/3 plus 1. After all, that's what my u was equal to. And this has to be raised to the 3/2 power. Now we need to evaluate this from 1 to 8. So I'm going to plug in 1 and I'm going to plug in 8. Kind of running out of room here, so I'm going to do my best to kind of squeeze this in. So if I plug in 8, let's see, I would have 8 to the 2/3 power plus 1. So 8 to the 2/3 power actually simplifies down, right? So remember, whenever you have something raised to a fractional exponent like this, you can kind of break it apart, right? We can think of this as 8 squared right? That's the 2-bit. And 8 to the 1/3 power, that's the same thing as a cube root. So we have to apply a cube root and we have to apply the squaring function. Luckily, you can do it in either order. So when I'm seeing this, I'm thinking about the cube root of 8. I know that, right? The cube root of 8 is 2. And if I take 2 and I square 2, right? 2 squared is going to be 4. So this all simplifies down nicely to just 4. Luckily, we do have calculators, right? The TI-30s, which is kind of a new luxury, I suppose, for the online class that we didn't typically get in previous semesters. So, of course, you could always just plug it into your TI-30 as well and verify that you get 4. So that's what happens when I plug in 8. Don't forget, though, that this is all being raised to the 3/2 power here. And then if I plug in 1, well, 1 raised to any power, such as 2/3, is going to be itself. So you get 1 there. Don't forget to add the 1 and raise all of that to the 3/2 power. And so my final answer at the end of the day, maybe I'm just going to put my final answer up, which is a bit strange, but it's going to be 5 to the 3/2 minus 2 to the 3/2. A nice, beautiful, positive number representing the length of that curve. Okay. As you can see, at the beginning of all this, right, we had really the difference was on the first problem, we had something raised to the 3/2 power. And here we had something raised to the 2/3 power. You can see that when you have something raised to the 2/3 power, it is considerably more difficult, right? We had a lot more algebra steps here before we finally got to the calculus. Unlike raised to the 3/2 power, that one goes pretty fast, all things considered. Okay, any questions here? I don't see any hands raised right now. Anything going on in the Q&A that we should talk about, Yuan?
Yeah, someone's asking where's the 3/2 comes from.
The 3/2. So it comes from, there's a couple of 3/2s that we've gotten, right? We have one in the exponent slot, and then we have one as a coefficient. The first 3/2 that we got as the coefficient comes from when you take the derivative of u in order to get du, and then you rewrite this, right? You need to solve and kind of exchange so that you can make your dy's into dus. You end up putting this 2/3 over onto the other side. And that act of, right, multiplying by 3 and dividing by 2 to get it onto the other side makes the first 3/2 that we see. The second 3/2 in the exponent slot comes from when we integrate the square root, which is u to the 1/2 power. Anytime you integrate, using the power rule there, you need to increase your power by 1. So it goes from 1/2 to 3/2. Do you think I covered it?
Yeah.
Okay. I don't think there was any other 3/2. Cool. Good. Well, with that, let's go ahead and move on to example number 3. Find the length of this curve here on the interval from 1 to 2. My eyes are playing tricks on me. This right here, I would probably recommend, if I saw someone had proposed this for a quiz or an exam question, really just to emphasize that this interval right here is an interval for x, right? It should be kind of clear, and we've grown up with y as a function of x for so long that probably most people would not get confused by this, but it would be a little bit better just to say that these are x values right here, right? For our independent variable x, right? X ranges between 1 and 2. Okay, so let's go ahead and set up our integral. Again, just as before, I'm going to do this bit a little bit fast. We're going to have the square root of 1 plus some quantity squared. And that quantity squared there is going to be the square root of y. I'm misspeaking and jumbling my words, right? We have a square root in this. But what we are squaring here is the derivative, right? So I need to calculate out the derivative. In this case, with respect to x, because we have a function of y with respect to x. So let's go ahead and take our derivatives here. When I take the derivative, let's see, a 4 comes down and I'm going to get x cubed. There's going to be some canceling that happens, right? The 4 and the 8 cancel a bit and you get just a half left over there. So I'm going to put divided by 2. And let's see, this one, it's a little bit more difficult. When I'm seeing this, I'm breaking apart the 1/4 as a coefficient, and then I'm looking as this at as like x to the negative second power, x to the -2, right? And so when you take the derivative of that, the -2 will come down, and you reduce your power by 1. So I'm seeing something like that. So let's go ahead and take one line to simplify that, and then we'll plug it in. So let's see, there's going to be a negative, and this will simplify a little bit to 1/2. And then I can also put this x cubed in the denominator there, right? Because it has the negative exponent. So this is what I'm going to go ahead and put inside of my square root. So x cubed divided by 2 minus 1/2. And the x cubed is in the denominator there. Okay. Well, same thing as before, right? I think it's going to maybe be nice if we take a line to try to simplify this, right? We got stuff inside of the squaring function. We got the +1. And I'm hoping that this isn't like, a terribly difficult integral. Hopefully, if we rewrite it in some good way. And so, okay, well, let's go ahead and try to simplify a little bit. And well, I need to FOIL this, right? Do the first, the inners, the outers, and the lasts, all that good stuff. Let me kind of break this off maybe to the side here. I have x cubed divided by 2 minus this 1/2 x cubed in the denominator. And I need to square it, aka multiply it by itself, right? So I'm just going to write another one. That way I don't forget to kind of do all the pieces, the first, the inners, the outers, and the lasts. And so let's go ahead, and if I was to do the firsts here, I would get x to the 6 divided by 4. If I was to do the inners, oh, that's nice. The inners, right? The x cubed on top and the x cubed on bottom kind of nicely cancel. And so this is just going to give me -1/4, right? Because we have 2's in the denominator there, so they multiply together to give 4. Okay, if I was to do the outers, again, things nicely cancel out those x cubes, and we just get -1/4. And if I was to do the lasts, so the last is this one right here. Let's see. Well, negative times negative is going to be positive. And then we're going to have 2 times 2 is 4, and x cubed times x cubed is x to the 6th. So right there. So let's go ahead and now plug that in. So we're going to have x to the 6th divided by 4 minus 2/4. So that's the same thing as 1/2. And now plus 1/4x to the 6th. And we see that there we have some like terms that we can still combine and simplify even farther, right? So instead of this 1 here and minus the 1/2, let's go ahead and combine these nicely and make plus 1/2. Now, at this point right here, there are 2 different legitimate ways that you can go in order to solve this problem. One is you can actually recognize that this right here is a perfect square itself. So just like back here, right, we had this bit being a perfect square. And when we expanded that all out, right, we see what we get over here in purple, right? If instead, right, you want this to be +1/4 there, right, you basically just change these to pluses. And you can see that this right here is a perfect square. So that means that you can rewrite this at this step as just the square root of this x cubed divided by 2 plus 1/2x cubed. And notice that I have the plus there rather than originally this was a minus. The reason why it became plus is again because we added this 1. So it changed it from -1/2 once we added the 1 to a +1/2. Right? And that's why we went from a negative to a positive. I'm, of course, very interested in this because perfect squares are great at canceling square roots. And right. And so this is what I'm going to use in order to cancel out this square root. Now, I told you that there was another way that you could also go about solving this. Maybe you don't recognize that this is a perfect square, right? And so the other way that you can go about solving this, and it does take, another step or so, but it's maybe easier to see, right, is that you get a common denominator, right? And so if you get a common denominator throughout all of this, let's go, maybe I'll take that a little bit fast. So the common denominator is going to be 4x to the 6th here. And let's see. So in order for the first bit to have the common denominator, I would need to multiply through by x to the 6th on top and bottom. So this is going to be x to the 12th. And then for the second bit here, let's see, I need a 2 and an x to the 6th. So this would be 2x to the 6th on top and on bottom for the 1/2 piece. And then for this last piece, it has everything, right? So this is just going to be +1. And remember, this would be all inside of a square root. So now I think it's a lot easier maybe to identify that this right here is a perfect square. And this right here, you can easily take the square root of, and you can get exactly to the same spot. So either way that you'd like, these are two kind of options in order to see that this indeed is a perfect square. Nicely cancels out with a square root. And that's what's going to enable us to actually evaluate this fairly fast. So when we have something squared and square root, right, these nicely cancel, especially because we're plugging in all positives here. So you don't have to worry about any absolute values or anything like that. Now we can go ahead and integrate this just using the power rule. So we're going to have x to the 1/4 divided by 4, but there's already a 2 down there. So it's going to be an 8 altogether there. And let's see, when we integrate this, I'm going to make the 1/2 kind of off to the side there. And remember, this is x to the -3. So we need to raise our power by 1. And then we divide by the exponent. There are new exponents. So this is going to be 1 divided by -2. And remember, we're going to need to evaluate this from 1 to 2, apparently. So again, maybe one line to simplify here, then we'll evaluate something like this. And I'll go ahead and take that x to the -2 and put it into the denominator there. And we evaluate this from 1 to 2. Okay, so if I plug in a 2 everywhere, let's see, 2 to the 4th power is going to be 16 divided by 8. And let's see, this is going to be 1 divided by 4 times 4 is going to be 16. And then if I plug in a 1 everywhere I see an x, we're going to have 1/8. And let's see, 1/4. And, you know, if this was on web work, you know, it would accept this. If this was a D2L quiz or an exam where you got to enter in an answer, right? You could go ahead and type that into your calculator and enter that. If it was a multiple choice and this wasn't an answer, maybe I would begrudgingly try to simplify a little bit. But I'm not super enthused about getting a common denominator and all that sort of stuff here. You know, that's a lot of arithmetic work there. Okay. So that right there is example number 3. Kind of another time, you know, something clever that you can do with a square root to get them to cancel to make the integral a little bit nicer, right? So again, we've seen maybe some u substitutions up here. This one, right, example 2 obviously was more difficult than example 1 as far as the u substitution goes. It took us a few steps and all that. For example 3, we didn't really have a u substitution, but we had a perfect square. So that's the other thing that can sometimes happen with these square roots. You get a perfect square, and then they evaluate fairly nicely. Good. Any questions? Let's see. I don't see anyone with a raised hand. Anything going on in the Q&A, Yuan?
No.
No? Okay, great.
Yeah, it's clear.
So then we can move on to example number 4. This one combines not only the stuff about arc length, but also we learned about hyperbolics, right? And you get a little bit of a real world problem. When you hang wire like this, you know, even though it kind of looks parabolic and whatnot, it's actually not. It actually is modeled by these hyperbolic cosine in this case. And so this is the actual accurate model for this. It's not just, you know, made up for, you know, our problem here, whatnot. So that's nice. And we have y as a function of x here. And again, we're asked to find the length, right, of the suspended cable, right? How much cable should you actually bring to this job if you wanted to hang wire between these two towers here? And so, okay, well, same thing as before. The length of our curve is going to be given by this integral from -20 to 20. Notice that these are my x values here, of the square root of 1 plus, and we're going to need to take the derivative and square it. So when I take the derivative of y here, let's go off to the side, right? dy dx. Take the derivative here. Well, the 20 is along for the ride. When I take the derivative of hyperbolic cosine, I get hyperbolic sine. Leave the inside alone. Then we multiply by the derivative of the inside. And the derivative of the inside is, well, 1/20th. So that's nice. These things kind of perfectly cancel out. And so, okay, we can substitute in then. This is going to be hyperbolic sine of x divided by 20. And it's being squared, added 1, put inside of a square root, all that good stuff. And so let's take one line to simplify this. -20 to 20. The square root of 1 plus hyperbolic sine squared of x divided by 20, all inside of my square root here. All right. And again, the question is, well, do I have to use trigonometric substitution, or is there some clever way that I can get this to somehow, can I somehow manipulate this using some algebra and whatnot to make this, a little bit easier to integrate? I see we have a raised hand, so I'll go ahead and take a question, or maybe it's the answer to my question. I don't know.
No,
Nito.
it was just a quick question about the bounds, rather.
Yeah.
So we have the -20 to 20, right? Can we have it as 0 to 20 and like multiply the answer by 2 at the end there? Because there's like a Calc 1 theorem or something like that we can do.
Because this is an even function, yes, you can. Well, let's see. Yeah, it's not obvious at this point. Maybe it is from the picture, right? That this is quite nice. And so you could say, well, if I can find the length of this bit right here, then I can just double it and have, the total length. So yeah, you can, because the picture was provided, but unless if you know something about the symmetry of the problem, then it's a bit risky. Does that kind of make sense?
Sure. Yeah.
Cool.
All right, for sure.
All right. So again, my question is there any way that we can simplify what we have in the square root here, or somehow rewrite it in order to make this easier to integrate? And so this is, you have to remember back to our chapter 6 days. In fact, let me use green here. And yeah, it seems like I see in chat here, a few people have this. Remember that we have the hyperbolic cosine squared of u minus the hyperbolic sine, squared of u is equal to 1. So when you have the regular old sine and cosine, our classic trig functions, remember it's cosine squared plus sine squared equals 1. But with the hyperbolics, right, they fit on the unit hyperbola. And so it's hyperbolic cosine squared minus hyperbolic sine squared equals 1. And so this is quite nice because you can go ahead and rewrite it. Hyperbolic cosine squared is equal to 1 plus hyperbolic sine squared. And now we can substitute this in, right? We can actually see that this is a perfect square. This is equivalent to hyperbolic cosine squared. And so we can go ahead and swap that. And so hyperbolic cosine squared. And again, we just leave the inside alone. Notice I was writing u there. It is true for no matter how complicated your inside is, you just kind of, leave it that same level of complicated. In this case, x over 20. Just kind of along for the ride there. We have this inside of a, now we have a perfect square, hyperbolic cosine squared inside of a square root. So these nicely cancel. Again, hyperbolic cosine is always positive, so you don't have to worry about any of these weird absolute values or anything like this when you cancel out your squared and your squared root. And now it's time to integrate. When I integrate hyperbolic cosine, I get hyperbolic sine. And if I was to leave my answer just like this, right, I would get some points off because I've forgotten, well, it depends on how you look at this, either a small u substitution, or if you're kind of thinking about taking the derivative and getting back to where you started, you can see that we forgot about the chain rule. So in this case, we need to multiply by 20 here. Again, either from a small u substitution, or if you took the derivative of this, right, remembering the chain rule, you need something to cancel out with that 1/20th. And so the thing to cancel out with that 1/20th is going to be 20 because it's being strung together with multiplication. So excellent. Now we can go ahead and evaluate at our endpoints. So if I plug in 20 into this, we're going to get hyperbolic sine of 1. And if I plug in -20, we're going to get hyperbolic sine of -1. And again, you can evaluate this in your calculator. There's the HYP, the hyperbolic button, I believe. Or, right, it's very possible if this was a multiple choice question that this would just be the answer. Or, right, you do have the definition, worst comes to worst, as far as the what hyperbolic sine is. So at very worst, you could have e minus e to the negative first divided by 2. And then here you would have what, e to the negative 1 minus e to the negative 1, which is 1 divided by 2 and multiplied by 20 here. So either way, well, in any cases, you can get the correct answer. Let's see. Ian, you have your hand raised. You have the floor.
Oh, I was curious what happened to. Oh wait, never mind. I realized I was confused why it was 1, and then I realized it was over 20. Never mind.
Ah, yes. Yep. No problem. Good. Anything going on in the Q&A, Yuan?
Nothing about this problem. There's one asking the previous one.
The previous one?
Yeah, the previous example.
Oh, okay. I must have not given enough time to type
Yeah.
questions.
Yeah, someone's asking how did you get these numbers in purple a little slower than you can?
These numbers in purple over here came from when I was trying to evaluate out carefully. Well, I guess, sorry, this is at the end of it. I was really trying to evaluate out this bit here carefully, right? And just FOIL everything, right? Because we had this binomial being squared. And whenever you have that, you have to do the first, the inners, the outers, the lasts, right? And so I was just kind of paranoid that I'd messed something up. So I wanted to take that a bit slow. And so that's why I kind of broke off to the side and did a little side problem there. Good. All right. Let's go ahead and at least peek at this next problem here. So consider this curve. This one has a nice natural log in it, x ranging from 0 to 1/2. Set up an integral that represents the length of the curve. So, okay, you guys know the drill. This is kind of a one-trick section, right? Just kind of applying the same stuff over and over again. Different functions though, so you kind of see there's, you know, all the different types of road bumps or kind of hiccups you can have kind of along the way with these sorts of things. So again, 1 plus a quantity squared, we're going to take the derivative. Maybe I'll just try to do this in line here. So when I take the derivative of the natural log, I get 1 over. And then don't forget about the chain rule. So, right, I left the inside alone, multiply by the derivative of the inside, and the derivative of the inside is going to be negative 2x. So that right there is my full derivative of y. So it just says set up an integral that represents the length of the curve. Done, right? So this right here, if you wanted to, you could, I'll take one line to simplify. I'm not going to go crazy with my simplifying. I think that's coming up in B anyway, but I'll just kind of make a little bit of progress here. Let's see, if I was to square things, let's see, the -2 and the x, that's going to become 4 x squared. And I don't know, I'm going to leave this 1 minus x squared just as is. I mean, we could try to FOIL that all out, but right now I'm not convinced that we need to do that yet. So, okay, I simplified at least. I squared the top and I squared the bottom. All right, part B, simplify the definite integral so that it is represented without any square roots. Okay, so I have to get rid of that square root. So just as before, you can kind of see we've been doing a lot of the same kind of algebraic maneuvers and steps and whatnot. When I see this here, my first inclination is to get you know, a common denominator, right? I want to get everything over the same denominator. That way they can kind of communicate with one another well. And so let's go ahead and get a common denominator. The way, of course, that we're going to do this is by multiplying this 1 by this 1 minus x squared quantity squared on top and 1 minus x squared quantity squared on bottom. So again, that way we get the same denominator here. Let's see, when we go ahead and do that, what we're going to have, again, the integral from 0 to 1/2, and the same denominator, this 1 minus x squared, all being squared. And so already I like my denominator, right? Because we have something squared inside of a square root. So those will nicely cancel. So I'm excited for that. Now in my numerator here, I have 1 minus x squared being squared plus 4x squared. So I'm still a little bit worried about my numerator. My denominator, I think we have under wraps. We can just go ahead and cancel out that square and that square root. And we're going to have this. So, okay, but what about the numerator? Well, I'm not looking, I don't see really any classic like U substitution or anything like this. Maybe this ends up being a perfect square if I was to expand it all out. It's not really obvious at this point, but it's really my only hope. And so let's expand this all out and see if we do end up getting maybe a perfect square or something. So, okay. The plus 4x squared isn't very exciting. I'll just kind of put that over there. Nothing really to do there, but this first bit, right, I need to FOIL it all out. I need to expand this. So maybe I'll give you the quicker version here. If I expand this out carefully, I'm going to get 1 minus 2x squared plus x to the 4th. So the firsts give me the 1, the lasts give me the x to the 4th, and then the inners and the outers combine very nicely to give me the negative 2x squared. And so just as before, you can see these things will actually simplify, and that negative 2x squared will become positive 2x squared. And so that gives me a lot of hope that this actually is a perfect square. Let's see, I see we have a raised hand. So why don't we go ahead and take a quick question. Jonathan, you have the floor.
Oh, so can you hear me?
Yeah, sure can.
Okay, thank you. So since both of them are in the numerator, or they are both like raised to the power of 2, can't you like just like make it like 1 power?
Oh, I wish that were the case. That would be wonderful. But no, sadly you can't. So for instance, the classic example of this, and there's actually several nice examples of this, but if you take 3 squared plus 4 squared, right? And right, so what you're suggesting is maybe that this is the same thing as 3 plus 4, right? That these things nicely cancel like this, the square root and the squared. And so that would be 7 altogether, right? If this works, this is what you're asking about right here. Are you allowed to do this? If this works, then we would get out 7. Now on the left-hand side, let's not do that. Let's just evaluate this out, you know, the normal way, quote unquote. And this is going to be the square root of 9 plus 16. So that's going to be the square root of 25, which unfortunately you can see now is definitely not 7, right? It's 5.
Okay, that makes sense. Thank you.
So yeah, sadly not. You can do this over multiplication, right? If this was 3 squared times 4 squared, this works out. You can do the square root to each piece, but the addition or subtraction ruins it.
Okay, I got it. Thank you so much.
Yeah, of course. Good. So let's see where we're at. We just canceled out the negative 2x squared along with the positive 4x squared to get a positive 2x squared. And we were hoping, right, if things work out well, that maybe that this right here is a perfect square. And so looking at it, I'm a bit more convinced that yes, this is a perfect square. And so I'm going to go ahead and rewrite this as what it should be, maybe one plus x squared, all being squared. So double check. If you were to FOIL this out, first the inners, the outers last, do you get back to this thing here? And the answer is yes. And it's of course very similar to this bit up here, right? But instead of a minus, we have a plus. Good. So now let's go ahead. Actually, I'll kind of skip a step here to some extent, and I'll cancel that square and that square root, and we'll have this. And so again, our task for this was to simplify the definite integral so that it can be represented without any square roots. So at this point here, there are no square roots remaining. And then finally, for part C, we're not going to evaluate this out, but we're going to identify which method of integration would you use to evaluate out this integral. Don't evaluate it. So just the method And this is where we'll need to think back and use a little bit of our maybe chapter 7 stuff. This one's more difficult here. So I have a vote for trig sub. And if before the square root canceled, I would be on the same page as you. I'd be, this is trig sub, definitely. But now that that square root's gone, kind of it's taken away the, the main reason we like trig sub. Let's see. Yeah, I'm starting to see it here a bit. That this is going to be a partial fractions sort of deal, that we can go ahead and split this up. So you're going to use, actually first, because the degree of the numerator is the same as the degree of the denominator, you're going to use long division and partial fractions. And you can see why I said do not evaluate this, because this takes some steps for sure. So long division and partial fractions was how you finish this one up, if you were so inclined. All right, with that, it is after 2:40, so that's going to be our last one here for the day. As always, please take a look at the problems that we didn't cover and try those ones out on your own. I will post the solutions to those here, hopefully within the next hour or so. We'll stick around if you have any one-on-one questions or whatnot. Otherwise, have a great day, and we'll see you on Wednesday for the beginning anyway, of our last section for the semester, right? 10.4. all about these polar curves, but this time we're talking about area and arc length for polar curves. So again, Wednesday starts the final section that we have in this class. So, all right, stop the recording.